So we are in 11.8. It's all about exponentials, specifically with e as a base. And what we like is the derivative of e to the x is just e to the x, right? It's the identity of calculus, right? But by the chain rule, if you have e to the stuff, the derivative is e to the stuff, and then you have to multiply by the derivative of the stuff, okay? So that's the trick. So we're going to do like 900 examples where you just do this over and over and over again, okay? So let's see. If we want f prime, the derivative of e to the x is just e to the x. This dude is power rule. This is not e to the x, right? What is this? Remember, e is just a number, right? So what do you do if you have e to the number? What did we do right here? We have e to a number. You multiply by the exponent and subtract one from the exponent, right? So we multiply by the exponent and we subtract one from the exponent, right? It looks weird, but that's all it is. This is e to the 2.7 whatever, right? It's just when you see e, you start thinking like x, like it's a variable. It's not a variable, it's just a number, right? It just happens to be a decimal that has no pattern because it's a transcendental number. So we use right, x to a number, right? That's all that is x to a number. So you use the same principle you used here. This, what is this? This is just a number, right? This is 2.7 whatever to the 10th power. What is the derivative of a number? What's the slope of 2? Right? How does this change as x changes? Number 2 doesn't change at all, right? The derivative of a constant is 0. This is a constant. There's no x's here, right? That's just a number. So the derivative of that is just 0, right? Does that make sense? Right? This is a wonky problem. They put a bunch of goofy stuff in here that you normally won't see just to test. Make sure that you recognize this is e to a number. I mean, sorry, let's screw this up. X to a number. This has an x, so it changes as x changes. This will change as x changes. You just multiply by the exponent and subtract one from the exponent. And this is just a constant. So there's no x's here. It doesn't change when x changes. So you just use your basic rules. All right. Here's e to the stuff, and there's an x in the stuff, right? So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. This one, this 5 out front doesn't change anything. We have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. All right. The 8 doesn't change. We have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative of this? 12x squared. Multiply by the exponent, subtract one from the exponent. You see functions like this all the time. This is a very type of function that shows up a lot, okay? So what could we do here? We could use the quotient rule Or we could rewrite this as 25,000 2 plus 15e to the minus 4x all to the minus 1. So we could use the power rule here, or we could use the quotient rule if we wrote it like that. Okay. How would we do this? Well, a number out front stays out front, right? And so for this guy, we have stuff to the minus 1. So we'll use the power rule. You multiply by the exponent, subtract 1 from the exponent. Now multiply by the derivative of the stuff inside. The derivative of 2 is 0. The derivative of this, well, we have our 15. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So we did a power rule, boop, boop, chain rule. We multiply by the derivative of the stuff on the inside. Is this. All right, we could do it that way, or we could use the quotient rule, right? Let's see, you end up with the stuff on the bottom squared. You have the stuff on the bottom times the derivative of the stuff on top, that's just 0, minus stuff on the top times the derivative of the stuff on the bottom. The derivative of the stuff on the bottom is, well, the derivative of 2 is 0. And the derivative of this is, well, 15e to the minus 4x times the derivative of the stuff. This is just 0. Boop. And you can see we have a minus 250,000. And then this guy, right? And then that thing to the minus 2 is the same as having that on the bottom squared. Okay. Then you just clean it up, right, with your algebra. You can do that either way. Does it make sense? You're following? Look at some checkpoints here. All right, A. We have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Here we have a minus 5, and then we have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Here we have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Another checkpoint. All right, this one, we have a function over a function. So we kind of need the quotient rule here. The quotient rule says you're going to have the stuff on the bottom squared. You're going to have the stuff on the bottom times the derivative of the stuff on the top. The derivative of e to the x is just e to the x. And then we have the top times the derivative of the bottom. The derivative of this is just 1. The derivative of x is 1. All right. And you can clean that up. Like you could factor out this guy, right? If you wanted to, you could be like, okay, I have a 12 plus an x and then a minus 1, both times an e to the x. So you could combine those, right? 12 minus 1 is 11. You might want to write it like that so it's prettier. All right, this guy, all right, we could use the quotient rule, or we could rewrite this. 15 plus 3 e to the, we could write that as a power to minus 1. So instead of using the quotient rule, we could simply use the power rule. Multiply by the exponent, right? Subtract 1 from the exponent. Now multiply by the stuff on the inside. Derivative of 15 is 0. The derivative of this, well, you keep the 3. The derivative of e to the x is just e to the x. Okay? Like derivatives, it's like peeling an onion, right? By the chain rule. Chain rule just gets you inside. Just keep derivatives, taking derivatives. Technically, this would be the derivative of e to the x is e to the x times the derivative of the stuff. Right? Well, the stuff is just x. This is just 1. So we never write that part, right? You just keep taking derivatives until you get the derivative of x with respect to x. All right, radioactive decay. All right, 100-gram sample of radioactive substance decays exponentially. The amount left after t years is given by A of t. Find the rate of change after 3 years. We need to know A prime evaluated at 3. So A prime, we have 100. We have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Of course, you could combine these if you wanted to, right? At this point, you just plug in the 3. You have negative 0.12 times 100. Well, what is that times 100? Multiplying by 100 just moves the decimal to the right twice. Replace t with 3. You're going to get a number. Plug that into your calculator. Right. 3 times 0.12 is 0.36. You get about negative 0.84. That's the rate of change. And it's in grams per year, right? Because t is in years, right? A prime is change in A respect to time. This is in grams. T here is in years. So your answer is in units of grams per year. Okay. 10 to the x. Here, well, we know what to do with e to the x, but this is 10 to the x. What are we going to do? Yeah. Yeah, there's a rule for it, right? Basically, we have to do a change of base. Let's see, how can we do this? My brain's hazy this morning. Oh, okay. Y'all familiar with logs? Logs are just the inverse of exponentials. So like e to the natural log of x is just x, or the natural log of e to the x is just x. Natural log is log base e. So they undo one another, right? So we can rewrite this guy. Here's your trick. The number 10 is just e to the natural log of 10, right? Because they undo one another. So this 10 to the x, just rewrite the number 10 as e to the natural log of 10. Okay? Makes sense. This is the number 10. This is the number 10. It's e to the natural log undo one another. So now we have a base, right? And an exponent to an exponent, you just multiply them, right? When you have an exponent to an exponent, you multiply. So that's the trick. Now it's base e. So y prime is, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But this is just 10. Okay, so the trick here is if it's not e to the x, if it's a different something to the x, you have to multiply by the natural log of the base. Okay. So here's the rule. And it works for everything here. Let's see. The derivative, you have a number to the x, right? You're going to get the number to the x times the natural log of the base. Okay. So think about it this way. If you have e to the x, this is e to the x times the natural log of the base. This is just 1. Okay, so it works, right? So all we're really doing is incorporating a change of base here. So, all right, so you get this extra step. You just kind of have to fix it, basically, right? Because e to the x looks like this. B to the x, they all look kind of the same, right? They all look, the exponentials, they all look the same. They all go through right here. So they're all changing at a slightly different rate. They're all exponential. So you just have to scale it, basically. You get your exponential back, but you have to scale it by the natural log of the base. Okay. And again, it's because of this. Exponentials and logs are inverses. So you just rewrite the 10 as e to the natural log of 10, and now you have it as the base that you want. E. So y equals 25 to the x. So y prime is going to be 25 to the x times the natural log of 25. Right. Again, how did that work? We rewrote 25 as e to the natural log of 25, and then to the x power, right? So y prime is e to the stuff is e to the stuff times the derivative of the stuff. But this is just 25. Right, which is the same thing we got up here, showing all the steps again. So if you can't remember this, right? Remember this, right? I always know that e to the natural log of x is x, right? Because they are inverses by the definition of logs. So by the definition of logs, I can figure this out. All right, now we need to do the derivatives of logs. So that was their way of kind of introducing logs. Let's see here. I guess I'd like to show you something here. Like if you have x cubed, the derivative is 3x squared, right? You have x squared, the derivative would be 2x. You have x to the first, the derivative is just 1. You have x to the minus 1, derivative is minus x squared, derivative is minus 2x to the minus 2, and so on, right? Just the power rule. x to the 0, that's just 1, right? You would have the derivative of 1 is just 0, right? But if you tried to use the power rule, you would have 0 times x to the minus 1 is just 0, right? It works. Okay? Let's see. Later on, we're going to have an issue when we're going backwards, right? When we're doing integrals, when we're going backwards, there's going to be a hole right in the middle. Okay. Let's see, what are we doing here? G of x. Okay, so a note on logs. Log base e, they write as ln. Right? Some students will mess this up. They'll think it's in. It's ln. It's like French or something. Logarithm natural log. Log base 10. Okay. If you don't write the base, if you just write log, basically what's the base, right? The different calculators have different presumptions. Okay, so be careful. Some programs, if you just write log, they might mean log base e. Usually you use ln for log base e, but some places they'll write log but mean log base e. Some mean log base 10. Okay, hopefully your calculator has the base. This is log base e. If there's any other log, they should write the base. Another log that shows up is LG, which is log base 2, because in computer science we have base 2, so log base 2 shows up a lot. Your three main bases are E, 2, and 10, okay? And usually your calculator definitely will have this one, right? It might have this one. It's possible it'll have this one, okay? So just be careful. It depends on where your calculator was manufactured as to the presumptions. If you just write the base, it's always clear, all right? This is always natural log. If you just write log, right? I don't know what that is, right? But you might see just log by itself, and they just assume that you know what the base is, right? It could be E, it could be 10, could be anything. So just be careful, right? Make sure you like look at your manual or whatever. Okay. Okay, and our properties of logs. Y'all remember your properties of logs? Log properties. So you have like, if you have a log of a, this would be like x times y. This would be log of x plus log of y. You can bust this out. And it's because logs are exponents. I know I said logarithmic functions are the inverse of exponential functions, right? But technically logs themselves are exponents, right? If I have a to the x equals y, right? If I take log base a of both sides, okay, these undo one another. Remember, logs and exponentials are inverses. So those undo one another, and I have x equals log base a of y. All right, where is x? It's right here. The x is the exponent, right? The exponent is a log. So when you see logs, logarithmic functions are inverses of exponential functions. But a log by itself, that is an exponent. So they follow the rules of exponents, right? If you have, if I have b to the x times b to the y, this is b to the x plus y. So when you're multiplying with like bases, you add the exponents. When you're multiplying, we're adding the exponents. See what I mean? If you have log of x divided by y, you have log of x minus log of y. So if you're dividing, you subtract. And this kind of comes from the power rule. For exponents, if I have b to the x to the y, this would be an exponent to an exponent, you multiply them, right? So if I have like log of x to the r, I can pull this out front. This is r log of x. And this is reminiscent. We have an exponent to an exponent. You can multiply them. So we're multiplying them, right? The log is an exponent, that's an exponent. You can multiply them. So those are the rules you can use for logs to simplify equations before you start taking derivatives. Okay, those three things. Okay. And this is just using this. What if r is -1? If r is -1, you can bring the minus out front, right? This is like plus. All right, so this would be like x times y to the -1, right? So really, there's just the two rules. There's really just this one and this one. Okay? This is a product of putting these two rules together. So let's see. Blah, 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 blah. Okay, they're proving. All this is summarizing the fact that the derivative of natural log is 1 over x, okay? Or x to the -1, okay? Let's see, I don't know if I want to go into the proof or not. Yeah, they're using the e to the g of x derivative. They're basically using this to prove this. If you're interested in the proof, you can get into detail. For y'all just need to remember that the derivative of natural log is 1 over x. So if you have the derivative of natural log of stuff, okay, well then you're going to get 1 over the stuff times the derivative of the stuff, okay? Just like the derivative of e to the stuff was e to the stuff times the derivative of the stuff. Since the derivative of natural log is 1 over the stuff, if the stuff is more than just x, you have to multiply by the derivative of the stuff. Okay? So that's it with the chain rule. Let's see. Oh, the other thing about logs is the stuff that you plug in has to be positive. Okay. All logs can't deal with negative numbers. Okay. So what do? They start off with which one of these? Differentiating with respect to x. E to the g of x equals x. Oh, where g of x is natural log of x. All right, so they're doing like e to the natural log of x is just x, right? Because these undo one another. So if you want to take the derivative of both sides, you get that. The derivative of e to the natural log, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And this is just 1, right? So working both sides of the equation here. What we're trying to do is solve for that, right? So therefore, if we're solving for this, e to the natural log is just x. So we have the derivative of the natural log is divide both sides by x, 1 over x. There's your proof. It's not too bad. We just start off with the definition of logs. They are the inverses of exponentials. and then you take the derivative of both sides. Boop, boop. Take the derivative of both sides, and that gives us that guy, which is what we want to solve for. That's just x divided percent by x. That's your proof. Okay. Just so you believe me. So let's do some practice. Here we have natural log of stuff. There's really parentheses here. This is a function. This is not L times N times 6 times X, right? This is natural log of 6X. They just leave the parentheses off, all right? I don't like that. But the derivative of natural log of stuff is 1 over the stuff times the derivative of the stuff. And you see those cancel, you just get a 1 over X. Okay. Here's a summary. Derivative of natural log is 1 over. You have natural log of stuff. It's 1 over the stuff times the derivative of the stuff because of the chain rule. So we have B here. All right, we have a function times a function, so we need to use the product rule. So we would have, do whichever order you want. The first function times the derivative of the second. The derivative of this would be 1 over the stuff times the derivative of the stuff. So that's the first function times the derivative of the second. So now we need to do the second function times the derivative of the first. And of course, you'd want to simplify this stuff. We have an x and an x. Cancels with the x squared, so we get a 3 plus, usually you like to write the stuff in front, right? Notice if I didn't put parentheses here, that just looks stupid, right? Put your parentheses. All right, because we want to know that's this times that the 3 is not inside the natural log. And all right, here's a big pile of stuff. That's okay. Derivatives are easy. We have the natural log of all this crap. Okay. Well, the derivative of natural log says it's 1 over the stuff. Here's the stuff. All right. 1 over the stuff times the derivative of the stuff. All right. Well, to take the derivative of the stuff, we have to use the product rule. So we can do it whichever way you want. We'll do the first function times the derivative of the second. The derivative of this guy, we have to multiply by the 5, subtract 1 from the exponent, now multiply by the derivative of the stuff on the inside. So that's the first function times the derivative of the second. Again, this one, the derivative of that, we had to do power rule and then the chain rule. Now we have the second function times the derivative of the first. And the derivative of the first would be a 2x plus 1, right? 2x and then a 1. And then you can multiply that all out, do the algebra and simplify it, make it pretty. Okay. 1 over the stuff, that's the derivative of the stuff. The derivative of this stuff required the product rule. Okay. Checkpoint. Okay. Y prime, natural log, derivative of natural log is 1 over the stuff times the derivative of the stuff. Natural log, it's 1 over the stuff times the derivative of the stuff. Natural log of stuff, you get 1 over the stuff times the derivative of the stuff. Here we have to do the product rule. So we'll have the first function times the derivative of the second plus the second function times the derivative of the first. Of course, we can simplify that, right? You good? It's just a lot of practice, right? It's pattern recognition. So you can do it quickly without making mistakes. I've done billions of these and I still make mistakes. It's practice. What's that? Pattern, yeah. It's basically getting your neurons wired to see these things and do it reflexively. Yeah. Just like recognizing people's faces. It's the same thing. You got to rewire your brain to be able to do this quickly. You ever met somebody with face blindness? Interesting people. Face blindness? I had a friend that had a head injury in football and gave him face blindness. So like every time he'd see you, he didn't know it was you until he heard your voice. You know, the voices, you know, that neural network was still intact. So like, he wasn't really sure who you were every time he saw you until he heard you or saw the, like the demeanor of which you move or something like that, you know, then he would know. What's this? Absolute value? Oh, natural log. See, I can understand why students think it's IN, right? Because the way they write it, right? This is LN, and we should have some parentheses here, right? Okay. Now, like I keep getting errors in my calculator. All right, so if y is natural log of absolute value of x, remember logs, whatever you're plugging in, it has to be positive. You can't plug in a negative number, it'll choke, okay? It's not designed to deal with negative numbers. I mean, in a real math class, you can plug in any number you want. You know, it gives you back imaginary numbers or complex numbers, is why they say you can't plug in negatives, right? So, but what if you want to have negative x? Well, then you have to put an absolute value. That way you can plug negative numbers in, but the absolute value turns to positive, right? So you might see that a lot. Then they say, well, the derivative of natural log is, well, 1 over x, right? Of course, x can't be 0, right? So that absolute value isn't really affecting anything, right? It's just allowing you to plug numbers in, but it's giving you the positive version. All right, so here we have a product, right? So we'll do the first function times the derivative of the second plus the second function times the derivative of the first. And of course, you can always factor out the e to the x, right? If you wanted to make it pretty. We don't like to repeat ourselves, so when you see something twice, you usually factor it out. Log. What base is that? I don't know. All right. We only know, so they're leaving it like generic here. I think in the book, they might be meaning log base 10. Let's see. Yeah, this is, so for this book, log without the base means log base 10. All right, for this book. All right, because they've already used ln for log base e, right? So if you see ln, you know they're using that for log base e. So if they just write log, you know that's not base e, because if it was, they'd have written ln. Okay, so that's a hint as to how to figure out what assumptions they're making. So like before, we knew to take the derivative of that. So we had to do a trick for what if we had this. We had to do a change of base. We're going to do the same thing here. We need to change it to a natural log somehow, right? How can we do this? This would be Let's see, we need to get to a base E, right? So log base 10. Let's read their, see their trick here. Here's their trick. Log base 10 is natural log of x divided by natural log of 10. Oh, change of base theorem on page 202. I don't want to go to base 202. I have 10 minutes. I don't want to get into it. How can we do this though? Let me take a minute to see if I can remember our change of base theorem. Let's see if I have b to the x equals y. If I take log base b of both sides, all right, those would just undo one another. But what if I do a different base? What if I did like base a? This allows me to pull the x out because I can do that. Okay, so I'm trying to change base 10 to a base e. So here this would be a 10, be an e. Let's see here. If I have 10, let's see. I have 10. I want to do a natural log. So the log base, log base 10 of x. We'll just use our formula for now. I'll think about it and get back to you. So if you're going to switch the base, you can switch it to any base you want. If I have a log base b of x, I could switch it to the natural log. I just have to divide by the natural log of the base. All right. It was the same reason why if we had a b to the x, right, I could change this to e to the x times the natural log of b. My brain not working this morning. So foggy. Anyhow, if you're switching from your base, whatever that base is, to the natural log, okay, you just have to divide by the natural log of your old base, okay? So just remember that. Log base b is going to be natural log of b. You just have to scale it. That's your change of base formula. Okay. So if we're going to take this guy, we would say, okay, well, this is the same thing as natural log of x divided by natural log of 10. Okay. So if I'm going to say, and this is just a number, natural log of 10. So f prime, we have this number out front, the number, and the derivative of natural log is 1 over x. Okay. I'm running out of time. I want to compare this though. This is by e to the x. There's that change of base. Where did I write it? This one. I'm going to put these together. Let's see. This guy. Y equals b to the x. This would be, forget it. Just remember our change of base formula for now. We only have 4 minutes. All right, so let's do our checkpoint. All right, so this guy, we have to do the product rule. So we have the first function times the derivative of the second. The derivative of natural log is 1 over x. And then we have the second function times the derivative of first. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Here we have a quotient. We could use the quotient rule, right? Or we could use the power rule. We could rewrite this as that to the -1, however you want to do it. We'll use the quotient rule here. So the quotient rule says you have the thing that's on the bottom squared. Let's put it like this. Over the thing that's on the bottom times the derivative of the thing on top minus the thing on top times the derivative of the thing on the bottom by the quotient rule. Now I have a word problem, 5 minutes. The person borrows $120,000 on a 30-year fixed rate mortgage at 5.7% interest. So R is 0.057. Person borrows, so there's our principal, and there's our time. Compounded monthly, N is 12. Then the required monthly payment is $696. That's our monthly payment. However, the borrower would like to pay off the loan early by making larger monthly payments. The actual number of months it will take to pay off the mortgage if a payment of P dollars is made each month is approximated by this function. So this function is giving us the number of months if you're paying P dollars a month, okay? So they give us the formula. I'm glad I don't have to derive that this morning. Find f of 710. Well, 700, you just plug in 710 here, right? And you know you have a natural log button. So that one's easy. What about f prime? Well, we'd have to take the derivative. When we say the f prime, we mean with respect to p, because that's the only variable. So we would have 211. The derivative of natural log of stuff is 1 over the stuff, right? Times the derivative of the stuff. What is the derivative of this? All right, well, the derivative of that by the quotient rule is the thing on the bottom squared times the thing on the bottom times the derivative of the stuff on the top minus the stuff on the top times the derivative of the stuff on the bottom. So we could simplify all this. 1 over stuff is the same thing as flipping this guy over, right? And then we have this. You could see that that cancels with that. 1 times that, that's just P minus 570. And then P times 1 is just P. So 211. P minus P goes away. Times minus 570 over P minus 570. So whatever, that's just a number. So it turned out to be something pretty simple, right? So f prime at 710 is negative 211 times 570 over 710 minus 570. It's just some number. So let's, for the sake of speed here, we're going to look at their answers because we want to be able to interpret these numbers, not just get the numbers, but we want to know what they mean. So if you pay $710 a month, you end up having 342.6 months. All right, that's the number that comes out. And here is our derivative. Assuming I didn't make any mistakes, we get that. All right, so what does that mean, the derivative? Remember, the derivative goes into the realm of marginal, right? This means that if you paid going from $709 to $710 a month, right? That will change the number of months that you have to pay by 1.2. You'll have 1.2 less months that you have to pay if you raise how much you're paying from 709 to 710. Or 710 to 711. Anyhow, that dollar difference a month in the end will change the number of months that you have to pay, right? By what the word marginal means, right? I just always the same thing every time. The marginal whatever. Yeah, increasing the monthly payment by $1 will shorten the length of time by approximately 1 month. We have to round down. I know we're out of time, but let's see what comes next here. They still have more stuff for us, so we're gonna have to finish this next week. We still have one more example for us. Hard to cover all this material so quickly. I don't know how they do it. Let's see. Let's take a peek into next week before we roll. I know y'all are in a hurry. If the syllabus is just open. And then it's a PDF file. There we go. 11/6, 11/7, 11/8. So next week we're jumping to 12/1 and 12/2. All right, so be prepared for that. I think we did enough where y'all can handle the homework though. All right, we're only missing one more example. All right, I'll see y'all on Monday. Get your My Math Lab done and your guided notes and all that stuff.